Hello and welcome back to the Code Athlete. This morning we will have a go at the round 1C of Google Code Jam 2022. If you haven't seen, I've already participated in round 1A and actually advanced to round 2. But I also, for training purposes, just took part in round 1B to practice for myself and to show you the solutions. And actually there were some comments that were found, especially my run through to problem C, very helpful because the analysis wasn't that detailed on why the approach they presented worked. So thank you for those nice comments, and feel free to, on every video I have, leave some suggestions if you want to see some other problem I haven't covered from some competition, and where maybe the solution was given but not well explained and you didn't understand it. You can ask me and I'll try do my best to solve those problems myself, record it, and present you maybe a solution that you can better follow through. Yes. Again, this video will have timestamps, so you can switch to the problems you like the most or find most interesting on how I approach them. Because I already advanced to round 2, I can't upload my solutions during the contest, so to check if my solutions, which I will implement now, actually work, you have to skip to the end of the video. Again, have a look at the timestamps, at the chapters, and I think you can find out pretty fast if my solution was correct or not. During the contest, I can only check with the sample cases. Okay, so again, 3 problems, probably the easier one, and then this one is the harder one. Let's have a look. It is a rainy day, indeed. I'm here in Germany again, and it's raining and gray clouds. The letter block is a wooden cube that has a letter printed on one of its sides. The font used for the letters makes the blocks have a clear orientation. That is, there is only one side that can be pointed down. One side that can be pointed up. Okay. You have built multiple separate towers so far. Now you want to combine all of them into a single mega tower. Choosing one of your towers as the base and picking up another one and stacking the whole thing on top of that. As an additional constraint for the mega tower, for any 2 blocks that have the same letter, all blocks between them must also have that letter. That is, each letter of the alphabet that appears in the mega tower needs to appear in one contiguous group. It's hard. For example, consider the following 3 possible mega towers. These are separate examples, not built from the same original towers. Yes. Leftmost 2 mega towers are valid. Yes, and the right one is C, not contiguous. Given the towers that you have built so far, can you stack them all up into a valid mega tower? Input. N is the number of towers. And then we have n strings representing the towers. It's a little bit like playing domino, because each sub-tower here we have basically a C end and an A end. And the C we need to connect to another C or something else if we don't have any other Cs. But yeah, and the A we can connect to A's, but we can not connect any B's to this. So there are some cases which are impossible, yes. Let's have a look here. Code needs to be connected to EL. MIG needs to be connected to code here on the left because of the C. And Jam needs to be connected to MIG because of the M. And I think the Z's we can put anywhere. So they put it here in front. Can I just print? I think we can print any. Yes, they actually say that those are the 2 valid. And the letters of SE are just uppercase. Or was it here specified? I think they're only uppercase. Hash code is impossible because of the two H's here, okay. And this is also impossible. Either way, you have the Y's between the O's or the O's between the Y's. And this one is impossible because of the two E's here. So we somehow need to check the starts and ends of strings. I think basically we can draw a graph. So let's say here we have this example OJ and JO. Then the only two letters that are present are the J and the O. And we have here a left and a right where we can connect. And this one here needs to connect from the right to a Y connection. This one here needs to connect from the left to a Y connection. This one here, this O needs to connect here to the right O, and this left O needs to connect to the right O. So this can represent our way we have to connect this, and because this graph is now a circle and not a line, basically we can say it's impossible. As soon as we have any circles in this graph, it's impossible. Let's do another example. I'm thinking about something where we have disconnected stuff. For example, if we have only code and the Z's, and we have the letter C here, the letter E here, and the letter Z here. And C connects here from the left to the right. This E connects here from the right to the left. And this Z connects here. And this Z connects here. So actually here we have a loop, but this is non-problematic because maybe this representation is not that cool. Because I anyway have to check also the in-between letters. For example, for the word hash, or here the word cat tags actually. Would have here the letter T, which can be connected. Then we have C and X. And that looks like it works alright. Because you have a line starting from here, going here through like this. But because of the letters A, it's actually invalid. How long can the words actually be? Oh, at most 10 only times 100. So we could put this line together, then concatenate everything. And then check the concatenated version if it's... I think we need a better representation somehow. Maybe you need to take every letter, so this is also, there's also an A present in this case. I'm thinking about just trying some stuff out here. Seems like it's just very implementation heavy. I thought if I can somehow get a nice shortcut, a very simple way to think about it, which makes the code very simple, but right now I'm just coming up empty. So reading in the strings, sorry, it's ER string function. And then I'm thinking about reducing every letter Yes, I will implement a reduce function. Reduce yeah. We need to take 26 letters into account. Reduce reductions. Reduce letter, and the letter will be the ith letter of the alphabet, and we want to reduce our reduction set. And with reduction, I mean, if I look at the letter A, I want to connect all the A's into one contiguous group and return a set. Actually, we return the set here again, which is then modified, and it will actually have all the letters A connected into one string. Or it will be empty. Let's say it will be empty in case it was not possible to reduce letter A, and then we can break into this. Let's actually do that. If reductions.size equals 0, this result is a string. And in the end, we can just because now we could still have, in this case, for example, code and ZZZ. If you go through all the letters, this list will stay the same because the set group will never be connected to the code because they have not any shared letters. And in the end, these two strings will be in the reduction set, and we can concatenate them in any way we want. So I could just go through the list. In most cases, there will probably be just one string left, but in case there are many, that means we can connect them in any way. So I will just go through the list. Yes, and then we have our result string. Just need to implement the reduce letter function now. Actually, this is silly. Letter and for string reductions. So we make 3 sets: rest, left, center, right. Now I will go through the reductions and see if it has the current letter we are looking at on the right hand side, and on the left there are different letters, or it's on the left hand side and on the right there are different letters, or center means if it's all the same letter, like in this ZZZ example. And no, let's call center where it's actually in the center, and left and right is different. And then we have all where it's all this letter. All same. Now we have to check what is a contains function. From C++23, there's actually a string.contains function, but I'll use the find then, I guess. Okay, if s.find letter equals string and pause, or equal to the end. What was it? Like this. Then the letter was not found. It means it goes into the rest group. And we can continue. In all other cases, the letter is present. Now we need to find all occurrences of letter. Actually, we can go through the string because it only has 10 letters. Yes. Sorry, I had to jump out there. I'm back. What was I doing? I was actually checking if our string now belongs into left, center, right, or all same group. So I think I will go through each letter. And if this letter is the one we're looking for, then L will be the position of the leftmost occurrence, R will be the position of the rightmost occurrence, and count will be just the number of letters we have. Now we can check if the left position up to the right position is actually bigger than the number of letters we have. That means we have some of our letters, then some of our non-letters, and then some of our letters. So this is impossible. So let's maybe make first the case where it's all the same. If count is equal to, no, let's make if count is smaller than left minus right. In the case where the size is only 1 and we have this one letter, then left is 0 and right is 0, so we need to compute right minus left plus 1. That's the number of letters we have between left and right. And if the count is smaller, that means we have a non-consecutive group, and we return an empty vector to indicate that this is impossible. Otherwise, we can check if it's all the same. That corresponds to if the left position is equal to 0 and the right position is equal to s.size minus 1. Then all same. And we can continue. What do we have left? Left, center, right. If left is equal to 0, we have a left group, and right is not equals to the other end, so it's a true left. Left. If right is equal to s.size minus 1, it is a true right. And in the other case, we have a group in the middle, so it's center. Now we have distributed our reductions into these 5 groups. If we have center, then left, right, and all same needs to be empty. And anyway, all of these can only have, well, this can have multiple values. Actually, let's first contract all same to one string. Actually, we can do this already here. We don't need this array because it's all the same letters. We can just put it into one big string. Like that. If left.size bigger equal to 2, we can return empty because that's again not possible. And if left.size equal to 1, can construct the contiguous string with, oh no, we need to start with the right because it means it's on the right side, yes. So write dot front, or the first element, doesn't matter, we just have one element. Then contiguous plus equal to all same concat. And then the left, if left dot size bigger or equal to 2, again it's not possible. And if we have a left element, we need to concatenate this. And now we need to check if there's a center element. If center dot size, again, bigger or equal to 2 is not even possible. So we can again turn here an empty array. If center dot size equal to 1, and that means we have a center string, but we also, if we have a contiguous string, that means this is also not possible. So in this case, we can also turn this. Otherwise, one of these is empty, either the contiguous string, because we didn't have right, all same and left, they were all empty, and we just had the center group. Then, so in this case, we can just again concatenate in the case where actually center is present. Zero. And if now our contiguous letter string is non-empty, we can put this into the rest group and return the rest group. And that should be it. That's the reduction. Oh, I first have to copy the test cases. Let's check if the solution works here. No. Ah, but that's the case where we can have any way around. So actually it wrote here the other solution, so maybe let's copy this into, no, it's the one and then this one here is produced by us because we go from A to Z, so Z will be concatenated in the end. And the others seem to work, and that was actually the correct solution, okay. So I think this should be fine, but it took over half an hour. That's pretty slow for the first problem, I would say. Let's see what others actually got here. No, no one was really fast actually. 9 minutes. Okay, it took us 3 times longer, but still. Actually, we would be right now in some, I don't know. Actually would be not too shabby. It would be right now even in the 204, top 204. Interesting. Let's have a look at Squary. Opening the code already. Again, the testing of my solution on the CodeJam server will happen at the end of the video. Look at the chapters of the video. Addition and squaring do not commute. That is, the square of the sum of all elements of a list of integers not necessarily equal to the sum of the squares of those same elements. However, this is true for some lists. One example is 3 minus 2, 6, because if we sum this, we get 9 minus 2 is 7, squared is 49. If we sum 9 plus 4 plus 36, it's also 49. Yes. Given a not necessarily squarey list of relatively small integers, we want to know whether it is possible to add at least 1 and at most k more elements such that the final list is Squary. And those lists are called Squary, yes. Each added element must be an integer between -10 to the power 18 is inclusive, and these do not have to be distinct from each other or from the initial list elements. The first line of the input is the number of test cases, yes. 2 integers, n and k, the number of elements of the initial list, and the maximum number of elements you may add. Second line contains n integers which are given. What are we supposed to do? It's possible to add at least 1 and at most k elements. Is this initial list actually? No, it's not necessarily Squary. We always have to at least add 1, even if it's Squary, okay? If it's possible to add at least 1 and most k elements, initial list. Why should we the set of numbers? And I think we can output them in any order, probably, because it's not specified. So here we have 2 numbers, -2 and 6. We need to add at least 1 number, and that's the number 3 from the example above. Yes. 2 numbers, and we are only allowed to add 1, and here it's impossible, it seems, because call that element x. The sum of the entire list is x squared. Ah, yes, because 10 minus 10 is 0. That's impossible. Okay, any integer is valid answer. Case 3. Because 0 plus x squared is equal to x squared. Yes. Okay. So here k is always 1, okay. And here we have a Squary list and we have to add a number. But we always can add 0, and that's safe. Yes, that's helpful, thank you. I add a 0 here, this doesn't change, and if I add a 0 here, that doesn't change. So we always can add a 0 in case it's Squary. Adding a 0 gives you the Squariness. Here we can add up to 12 numbers. There, adding 12 ones. Okay, a very mathy problem, I guess. I think we have to find some kind of interesting identity about this. So we have the sum of AI squared and the sum of the AI squared individually. And one can now be bigger than the other. What happens if I add an x? If I add a single element, to the left-hand side we have sum AI plus x squared. I want to give this letters here. Let's call this A and let's call this B, and let's try to rewrite this in terms of A and B. So this is equal to sum of AI squared plus 2 sum of AI times x plus x squared. So this is equal to A plus 2 times, let's call sum of AI s times x plus x squared. That's the left hand side, and the right hand side we have sum of ai squared plus x squared, which is equal to just b plus x squared. And with every x we choose, we could try to decrease the difference between a and b as much as possible. And the value by which we change the difference is actually this 2 times s times x. Because here we have still a and b on the one side and on the other, and we have also x squared on both sides. And the s is given, so finding an x is pretty easy. So actually with k equals 1 it's quite easy, because we've computed here the k's, and this has to be exactly the difference between a and b. We can just check if 2s divides the difference between a and b, and then x is just a division basically of a minus b divided by 2s. Yeah, let's actually write this. If we want to have a plus 2sx plus x squared equal to b plus x squared, then we need to have 2sx equal to b minus a, or x equal to b minus a divided by 2s. This gets a bit harder if we can take multiple values of x. I'm thinking if we can always do it with 2 values. Maybe let's write this as x, not as one element, but as a group of elements. So we have sum of ai plus sum of xi squared. That is equal to a plus 2 times s times, let's call this big X. Big X is the sum of the xi. And y is the sum of the xi squared. Okay. And we have here plus x squared. We can actually, I'm just realizing we can actually write s is equal, or a is actually s squared, like this. Yeah, okay, let's rewrite all of this because I'm getting confused otherwise. Let's call the sum s, and the sum of the squares a here in this case. Then this is s squared, 2 times s times x plus x squared, and this is now a plus x squared. We have a minus s squared, and here again a minus s squared. Because this needs to be divisible in this case by s, and s squared is divisible by s, actually a needs to be divisible by s, which is already interesting. But okay, let's have a look at this one here. So we call sum of the xi is, can't use s again, right? T, and the sum of the xi squared is x. Then this is equal to s plus t squared, which is equal to s squared plus t squared plus 2 times s times t. And right hand side is sum of ai squared plus sum of xi squared, which was a plus x. We want this to be equal s squared plus t squared plus 2 times s times t equal to a plus x. And what we can initially observe is basically this s squared minus a, which is, or here we had a minus s squared, maybe, let's write it in that way. Oh no, let's put it this, s squared minus a. And we can put on the other side x minus t squared. And then we have still here this 2st. Because this only depends on the ai's and this only on the xi's. And what is the fastest way to construct this? One interesting observation, if we change the sign of all the ai's, then the sum will be basically minus sum, and the a will be unchanged. So here we can basically choose this sign freely. I'm losing the information that this a and this x are actually coupled. Yeah, this squared something. Another approach. Let's just look at any list ai squared equal to sum of ai squared. We can rewrite the right-hand side to sum of the binomial formula, sum of ai squared plus 2 times sum of I smaller j ai times aj. And then we can subtract this term, and we need as a requirement for our Squary list that 2 times sum I smaller j ai aj equal to 0. But we can leave this 2 away if we leave this 1 smaller j away. I think this is maybe a simpler condition. This is a sum sign. Look like 1. Sorry. But I is unequal to j. This is still important. Because those are actually exactly the squared terms which we moved here. This is the condition. And that's also not really helpful. I have the problem that we need to prove somehow that if it's impossible, we need to actually know that it's impossible. But actually I'm seeing here no impossible anywhere, so maybe with 2 values it's always possible? Can that maybe be? Do we just have to restrict ourselves to 2 values? It seems like we get a lot of freedom actually. With 2 values. Let's write this again for two values. I'm not sure. So left-hand side would be the sum plus x plus y squared. That should be equal to a, the sum of the squares, plus x squared plus y squared. Left-hand side is sum squared plus x squared plus y squared plus 2 times s x plus y plus 2 times xy equal to a plus x squared plus y squared. And again, we can cancel x squared and y squared, and we can put s squared on the other side. So we have 2 times sx plus y plus 2 times xy. This 2 we have already bracketed. A minus s squared. Is a minus s squared actually always divisible by 2? If s is odd, yes, I think this is always divisible by 2. Otherwise, I would have said in the case where this is not divisible by 2, we can't do it with 2 elements. Maybe we need more. Maybe there's always a factor of 2 actually. But it's always divisible by 2. So anyway, let's not discuss that. But the question is, we have here a given difference. We can divide this by 2, and we have still a given integer difference, and we have a given s. Can we just choose two values, x and y, which will satisfy this condition? So s is given, and we have the values x, y, which we can choose. Let's maybe write this in this way. Equal to some delta, which is a minus s squared divided by 2. I'm not sure if that's always possible. What if we set this x plus y as close to delta divided by s as we can, so x times y has to be quite small. Can we rewrite this maybe? X plus s times y plus s is equal to xy plus x plus y times s plus s squared. So this here is actually x plus s times y plus s minus s squared equal to delta. And this works, right? Because we can compute this term we can factorize it. We can always say this is equal to 1 times delta plus s squared actually. That's enough. And then we can set this to 1 and this to delta plus s squared. Because we can always choose the x and y in that way. Just have to make sure that s maybe cannot be big enough. Because we are only allowed the values from minus 10 to the power 18. But we are given that EI, so S smaller or equal n times 10 to the power of 3 is smaller or equal to 10 to the power of 6. So s squared is smaller or equal to 10 to the power of 12. Delta is also smaller than or equal to 10 to the power of 12. Yes. So this should be fine. This should work. Nice. So we have to just handle the case of k equals to 1 and the case of k bigger than 1. Okay. If k equal to 1. We need here the default value mode because again impossible, and we make result a vector of values. Result.clear. If k equal to 1, we have to look at our formula for a single x. We need to compute this. This is, as we've observed, always divisible by 2. So first we need to calculate the values a and s. So a equal to 0, s equal to 0. Like this. Let's compute delta, because delta is a minus s squared. We need that also. A minus s times s divided by 2, which is always given that it's divisible by 2. And now we can use that also up here, because this is again the delta term divided by s. If delta modulo s equal to 0, then result of pushback delta divided by s and return. Actually, in any case, we return here because this case k equal 1 is now finished, and if this was not the case, then we have an empty result, which will trigger our impossible, because then it's not possible. And in this case, we can always do it, and we have x is equal to x plus s is equal to 1. So we have 1 minus s, right? And y is equal to delta plus s times s minus s. Actually, we can directly push back this into the result. then this should be also fine. And I need to compute copy the test cases first. And I concatenate those. So now we have 7. This is very wrong. Well, case 1 got solved correctly with the 3 here. In case 2, got a floating point exception. Why do we have floating point values after all? We should not have any floating point values. Is this delta used somewhere else? No. What? Never seen this. Where do I have floating point values? Are you crazy? Is it the reading of values? Minus 10, 10, yes. A and S is computed correctly. Oh, if S is equal to 0, then yeah, we should check if delta is equal to 0. Delta is equal to 0, then we just push back a 0 and return. And in this case, if S is equal to 0, then we just return because we can't find a solution as well. Now we get an answer, yes. Case 3, it was that we can have any integers, so 0 is also fine. And case 7, this one here, we can actually have a 0 because it's a single value, yes. So this looks all right. Sadly, I cannot test it again. Took us roughly half an hour to solve this. Actually, I will change these values here. And we have to check this in the end again. Look at the timestamps, and we have 1.5 hours left for problem 3, the hardest one probably again. So we have M machines. Each pair of machines is connected by a link. Each of the link is given a unique integer priority. We have this many links and this many unique values. Each machine routes traffic according to those priorities. Fortunately, the routing algorithm is too aggressive and will route all traffic from a machine through the highest priority link connected to it. This may make some groups of machines isolated from others. Good. Formally, we say that a machine M uses a link L if and only if L is the highest priority link connected to M. We also say that a link is active if it is used by at least one of the two machines. Given the link priorities, the original network becomes partitioned into disjoint intranets. Two machines belong to the same intranet if and only if there is some path between them using only active links. Okay, so the 1 uses the 6 and the 2 also uses the 6, and those are all inactive from the perspective of 1 and 2, and from the perspective for 3 they use 5, and they all get deactivated. Okay, this 4 is active because of this one here. It's the highest number here. Yes, for example, as seen in the left image on, yeah, here everything is connected. Part of the quality assurance team, you're investigating the extent of the problem. You're interested in knowing the probability of there being exactly k intranets if the priorities are assigned uniformly at random from among the You're investigating or interested in knowing the probability of there being exactly k intranets if the priorities are assigned uniformly at random. This sounds again very mathy, math heavy, this problem. So I think this round will be one where math people have a big advantage over programming people. And I'm more mathy, I would say, but well, problem 1 took me way too long. But it seems everyone took actually quite long on problem 1, so for each test case, output one line containing x, y, where x is the test case number and y is the solved probability computed model of the prime, which is defined precisely as follows. Represent the probability as an irreducible fraction. P and q being non-negative integers, and minimize p plus q. Yeah, whatever. Never heard this formulation which minimizes p plus q. I mean, irreducible fraction is a well-defined term in itself, and it's not usually defined by minimizing p plus q, but I guess it's equivalent. Then y must be equal to p times q to the power of 1. Q to the power of minus 1 is the modular multiplicative inverse of q with respect to the modulus. It can be shown that under the constraints of such a number y always exists and is unique. Yes. Except for q equal to 0. Which, of course, if we divide p by q, this cannot really be the case. But if q is equal to 0 modulo this number, so for example, if q is equal to this number, then q is 0 and does not have a multiplicative inverse. So that's a bit strange. Or would you say 0 is a multiplicative inverse of 0? No, because, yeah, 0, yeah, it's not well defined in that case. It's a bit strange, I would say. It's 3 divided by 7, but then you have to compute this basically modulo. Maybe we can have a look here and understand this and why it's only 3 over 7 if we have this many combinations actually. So let's call M. So we have always given the number of machines and the number of, okay, the number of intranets we're looking for. We want to look for exactly 2 intranets. In test cases do we have? Only 50. Let's call M equal 5 machines and denote a link. Assume that the priority of links is 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5. Then machines 1 and 2 use link 1, 2. Machines 3 use link 1, 3. And machines 4, 5 use link. Thus, 3 links are active and there are 2 intranets. Since k equals 2, this situation counts the answer. We can find that there are little ways to assign the priorities to have exactly 2. Okay, they're not really explaining how this part works. Okay, let's think a little bit about this on paper. First thing I've already thought about is the case where we have k equal 1 intranet, basically. And one interesting observation is there is this highest ID link, basically, somewhere. So for every active link, we can actually, for every node, we can actually mark the link that gets activated by it because it's a maximum. And the maximum edge will be activated by both this node. So let's say this is an active link and it will be activated by this one and by this one. And then other links, there might still be other links which also get activated by both nodes. And there are links which get only activated by one node. So for example, this edge here was also activated by 4 and by 3. And then there might be edges which are just activated by one node and not by the other. This is, for example, the case with this 4. Which is activated by the 4, but not by the 3 because the 3 activates the 5. And the same for the 5, it's not activated by the 2, but 6 is activated by the 2. 6 is in fact the highest here, which is then always activated by the 2 and the 1. What I'm trying to say is, we have one edge which gets activated by 2, and then more edges maybe, which are either activated by 2 or by 1. But each node can only be responsible for one activation. So we have at most, if we have m nodes, we have at most m minus 1 active edges. And let's say actually this here is count A, and this type of connection where only one is responsible is count B. We have this formula that A is bigger than 1 at least, because the maximum edge is of this type. And then we have the number of edges is actually a plus b. But we have the formula, number of activations here, the small dots, we have 2 times a of the small dots plus 1 times b. And this needs to be exactly the number of the machines. So you can see this is the number of edges. And this, because of this formula, it's equal to m minus a again, which is, because a is bigger or equal to 1, this is smaller or equal to m minus 1. Why is this interesting? Because if we want to have just one component, one intranet, and they all need to be connected, such a network needs to have at least m minus 1 edges or more. But because the upper bound is m minus 1 now, we can actually say we need to have only exactly one of this type and the rest needs to be of the B type. You can see this again here. Like here we have just one intranet, but it's really just only the maximum which is connected, which is double activated basically, and everything else is only single activated. So A is equal to 2 and B is equal, A is equal to 1 and B is equal to 2. And as soon as A gets bigger, so in this case A is equal to 2 actually, we need to have one more intranet. This is some high-level observation. How do we actually compute probabilities? Is this helpful, this insight? I am not sure. How big are the numbers? We have 50 test cases, 60 seconds, which is quite a lot, but a lot of machines. Can we do some kind of recursion of the way maybe p of, I don't know, m half or m minus 1 and k minus 1 or so, or k half? Or do we need to sum over all k's? I think we need to somehow define some smart recursion, dynamic programming, I'm not sure yet. Is it somehow, and we somehow need to have a look at the largest priorities. So let's say we have here maybe 5 again, with 10 edges. And this could be a 10 maybe, this could be a 9. I want to create 2 intranets now. And for each intranet we can have a look at the largest priority link. And we can get there by always wandering along the largest link. So let's say this intranet has as a largest link then the 8, because we put the 9 already here, and this one is a 10 intranet, and this one is the 8 intranet basically. Now this one activates 9 because it doesn't have access to 10, so we have here the activation. This node activates the 10, this one activates the 10, because 9 and 8 are here, this one has to activate the 8, and this one also has to activate the 8. And that means everything else we put in here will make sure that we have 2 intranets. Is it always a tree diagram? Can we have circles? I don't think so. Let's assume we have a graph where the activated links somehow produce a circle. I don't know, like this. Let's say this node activates this link, which means this number is bigger than this one, like this. If this node also activates this link, again, because we have the circle, and each of the edges can only be activated by one of the nodes, and if we have one edge actually being activated by 2 nodes, the other 3 edges can only be activated by 2 nodes, which can't work. So we know that if we have like the activation at this point, we need to also have the activation at this point, and this point. But then if this activation is here, this means also this is bigger than this edge, this is bigger than this edge, this is bigger than this edge. And then we have a circle of inequalities which can't fill. Like if I have 3 here, this needs to be like something like a 5, 7, 8, and then this last one is broken. So we can never have circles. We always have tree structures. And tree structures, well, with disconnected graphs. And actually, in that case, the number of edges directly corresponds to the number of intranets. So we can say the number of edges plus the number of intranets is always equal to the number of nodes in this case. Again, let's look here. We have 2 edges and 2 intranets, which is 4, the same number as we have nodes. And here we have 3 edges and just 1 intranet, so here it's also 4. And the reason for this is, let's say we have some, I don't know, connectivity graph. Like this. Can we actually even have this kind of branching? I think we can, yes. Because this one could have this activated, this one could have this, and this one could have this activated. Something like this should work. So maybe we have this graph, this subcomponent intranet, and I don't know, maybe something like this, just a simple line. We can now basically connect these subcomponents like this, and then we have our complete tree with the complete graph. We needed to draw exactly 2 lines because we have 3 components, so we added k-1 lines. Plus the initial number of lines is now equal to a graph which connects m nodes, has always m-1 edges. And from this we can reduce this -1 and get exactly this formula. And we have this formula for E based on the number of double activations. So E is actually m-a. This is m-a. Or in other words, now we can reformulate this, k is equal to a. So we have exactly the number of intranets. This is exactly the number of double activated edges. And again, we can see this here. The 6 was double activated and the 5 was double activated. 2 double activations, 2 intranets. Here we have the 1 double activation of the 6. These are all only single activated, and we have 1 intranet. So we really just need to figure out how to compute the probability of having exactly k double activated edges and the others being only single activated. How do we do that? Still not an easy problem, but it feels already easier than looking at some kind of connectivity or so. Now we could look at the number of different sets. Like we have in total, for the complete graph, we have m times m minus 1 half edges. And out of those, we want to select k that get double activated. So this is a large number because k can be m half. Yeah, this can be very large. We can't go over all the combinations. We need to do it smarter. Maybe thinking about recursion again, what can I reduce from this problem so that we have a new reduced problem where the double counts have not changed? What is if I remove the largest edge? I know the largest edge is double activated. So in this left-hand case, here we have the 6 here, and we remove this one, we have just 1 to 5 edges. Now we want k, because we have removed one double edge, and we got k as input, we need k minus 1 other double activated edges. So the next double activated edge could be potentially 5, which could be basically in the graph not including those two edges, which would be down here, which needs to be here then. Or the 5 could be somewhere along these lines. But those wouldn't get double activated because these already have the 6s used. Actually, these edges, these points, they cannot activate anything anymore. So we have only these 2 points which can activate, and if they need to double activate, the 6 needs to be here. Actually, this might be really, maybe we can decouple the actual values from the location of the. So if we have like a big graph, let's say with, I don't know, 6 nodes, and we want to, or 7 maybe, and we want to have 2 double, no, let's say 5, and we have 2, we want to have 2 intranets and therefore 2 double edges. We can say it's this one, and we can say it's this one, just the first 2 and the third and fourth. And then we can compute the number of rearrangements, or actually, how do we actually count different graphs? By keeping the nodes fixed and rearranging the priorities, right? Yeah, but anyway, from any solution where we have 2 intranets, we have also two double activated edges, and we can always rearrange basically the nodes to be lying in this configuration. And what is now the requirements for the values of these priorities? these here have to be smaller than this value, these here have to be smaller than this value also. And same goes for here. This one has to be bigger than all these 6 values. This one has to be bigger than all these 6 values. We can also say, we can always normalize our cases to the one where this has the largest. So this is basically A, and this is B. Then we have the next double edge basically might be C here in this case, if we need it. We can always put them, arrange the nodes in this way that we have here the largest, here the second largest, and here the third largest. Let's call this maybe A3, A2, A1. Because now we know A1 has to be bigger or equal to, because we have here like m-2 edges going out, and we have here m-2, and those are all different. So we have m-2 times 2. And needs to be actually really bigger or bigger equal to this plus 1. And if it's actually, if A1 is actually exactly this number, we have also fixed all these edges here. Now, can we write condition for A2, because A2 needs to be bigger as A1, because we wanted to sort it like A1 is smaller than A2 is smaller than A3. But A2 also needs to be bigger than all these M2 numbers and these M2 numbers, and they are, there's only 1, 2, 3, 4 sharing numbers here, and the others are all bigger. So A2 needs to be also bigger or equal to basically 4 times m-2, because we have 1, 2, 3, 4 nodes, minus the 4 connections which are double counted, plus 1. So A2 needs to fulfill both of these conditions. And actually there's another condition, which is that A3 needs to also be fit above A2. So for example, if A1 is close to this lower edge, A2 cannot just be A1 plus 1. It needs to be much bigger. But if A1 already is quite high, then this lower bound doesn't matter, but this one is important. How do you count those number combinations? Because now I'm thinking about, what if I can compute the number of combinations for choosing these values A1, A2, A3? And multiply this with the number of being able to rearrange those nodes into any position, so I get any graph. And that needs to be also multiplied with the number of combinations I have for choosing these other values, basically. But I think I can choose them quite freely after selecting A1, A2, and A3 with, no, I cannot choose them freely. That's bullshit. Anyway, A3 has to be the largest edge, because this one has to be bigger than all of these ones. Yeah, because the largest edge is double counted, so it's part of these A values, and because we sorted them, A3 is actually equal to m times m minus 1/2. So this is the maximum. There's basically no free choice for A3. But then there's a free choice of all of these. And can they be really anything and it can still work with A2 and A1? I think so, yes. Or no. If we choose only the largest values here, then A2 cannot be big enough to be bigger than all its neighbors. Or, in another word, the second largest value, for example, cannot connect here, because otherwise, it could connect here, I guess. If I throw this one out with this node and all these connecting edges, then I have a subgraph, which is too smaller, and where A2 needs to be again the biggest index if I reorder basically my indexes to close any gaps which were created by removing these edges. So I could compute the number of combinations, intranets. So because I've removed one intranet, I need k-1 intranets here now in the subgraph with 2 less nodes. I can count the number of combinations, and now I need to merge this with the largest edge. What do I need to compute this merge? Biggest input again. K is roughly 10 to the power of 5. This is quite large. So we could have K in the order of K values for A1 to A2 to A3. Because somehow I'm thinking I need all of these A1, A2, A3 for computing AN basically. I mean, AN is then by definition always the largest value, but to compute the number of combinations for these edges here, which I need to add, because I need to make sure that these here are all smaller now than A2, or in other words, I need to increase basically this edge here so that they fit all below. Hmm. This is possible to compute this recursively. If I think of adding this edge, the largest value, it is by definition double activated. I just need to make sure that everything here stays double activated, which was double activated. Can I do the compute of combinations without knowing these values which they had? I think that's not possible. Because they could be very large and then they could go all below, or they could be very low. And then there's much less combinational combinations I can choose from to activate these links. That's still a hard problem. Not sure how to approach this. I mean, it's interesting that we actually get here 3 out of 7 probability, or with 5 and 1, a 4 out of 7. Where does the 7 come from? Because the number of combinations was... I compute the number of edges, which was 10. For a 5 node graph. I have 10 edges and I can rearrange them in any way, so 10 faculty possible combinations. In case 6, it's only 21. So there seems to be a lot of symmetry which one can use to reduce this number of all permutations down to, it seems, in this case, only 5 relevant ones. 7 relevant ones that can be distinguished. Is it maybe not inserting the biggest one, but inserting the smallest one? Because for this we just need the value of the lowest previously one, which would be this one here. It's just one value instead of all the k values. And we can say, okay, this needs to be lower than this one. By definition, as the number of edges I add, I can always choose a value for A1. And these need to be all lower so they don't interfere with the existing double edges. So I just need to check how many values I can have for A1. Now, well, if A2, for example, is 10 in the subgraph before adding this edge, then there could, oh no, this needs to be on smaller. So A1 I could make Okay, if I add A1, I'm adding de facto how many edges? We're going from, previously in this subgraph we have m minus 2 edges, m minus 2 nodes. So we're adding 2 times m minus 2 nodes plus this one, the self-connecting edge. And those edges are all smaller or equal to, I mean, this one is itself, of course, included, and the 2 m minus 2 edges here, they all need to be smaller than this value. Now, for example, if A2 is n in the subgraph, we have somewhere else a 9 maybe. But this 9 would never be then connected to the A1. We could increase it. I mean, in other words, there are 9 edges smaller than A2. And now we have these additional edges, which are also all smaller than A2. So A2, yeah, all of these edges which we are adding are smaller than A2. So A2 needs to then become 2 times M2 plus 1 in the new indices of this graph. And now A1 can be any value larger or equal to this one, and smaller or equal to this one. This is the number of possibilities we have for A1. And for each of those, the number of combinations for assigning numbers to this is actually, this might be actually computable. Because if we, for example, select the lower bound for A1, this means, well, we have to select the values from 1 to 2 times n minus 2 for all of these edges. There's no degree of freedom, except for permutations, of course, but that's like 2 times m minus 2 faculty, basically just number of permutations we have for all of these edges. If A1, for example, is 1 bigger than this, if that's allowed by A2, A2 could be, of course, here a 1, and then this would be not allowed, but it's a 10, so it might be allowed. And in that case, we have for the first edge 2 m minus 2 plus 1 possibilities. Then for the next edge, 2 times m minus 2 plus 0 possibilities, and so on. So this is exactly 2 m minus 2 plus 1 faculty. And then there's one value left, which will be one of the values of 1 to 9. Which we can rename to one of the values which we skipped. And if we have like this 2 times bigger, then we have 2 times m minus 2 plus 2 faculty possibilities divided by because we only take the first, we need to divide this by then 2 faculty. So this is actually also divided by 1 faculty or 0 faculty, which is in both cases 1. That's why I didn't write it. Here we have 2 faculty because those are the numbers we skipped. in which we can't interchange between these edges because they're already fixed here with the 1 and the 2 numbers in this case. So the question is, can we sum this kind of n faculty over 0 faculty plus n plus 1 faculty over 1 faculty plus n plus 2 faculty over 2 faculty plus and so on. And this upper value k is given by basically this 10 here, how high the A1 can get. And this, because this k can become, we need to think about how often do we need to make this recursion. And the number of recursion steps, or let's say it in different words. We have some kind of dynamic programming approach which takes the values m and k, which are exactly here our input values. And to compute the value mk, we need to then use the value of m minus 2 and k minus 1. But we also need to know the lowest value here. So this would be another parameter for the dynamic programming. The lowest possible value, and those can be quite a lot of values actually. Yeah, it could be m times m minus 1/2, right? I mean, it could not be all of them, but m squared is kind of the order for what this would be. With this m and this k. But do we need to compute it for all k's? Maybe not. But still it would be of the order m cube, which is 10 to the power of 15, which is much too big. And then for every such element, well, actually then we don't need to compute the sum, because we have the fixed lower value for the next one we want to add. Oh, I need to write this formula down. Maybe we can see something to exploit to avoid the include. So dynamic programming of m, k, and a current value a, we call it 1, right? It's equal to a1 is the lowest double activated edge in this case. And this is equal to how many combinations I have for marking for selecting this A1 position in the nodes. Yes. How many possibilities are there for the selecting 2? It's just m over 2, right? Times for the subgraph from the selection here, we can compute how many possibilities there are to get k minus 1 intranets. But here I need to sum over all possible A2 values. So here comes the sum. Minus 2, k minus 1 intranets, and a2 as the lowest value. And then if I have selected a1 and a2, what is the possible number of combinations to write to these edges? It's, I think, a1 minus 1 faculty divided by how many edges there are which are lower than a2. Before adding these two edges, right? So the new a2 value would be, after the merging, a2 plus 2m minus 2 plus 1. Oh, I can just say a1 minus 2m minus 2, I think, faculty. So in the case where a1 is equal to 2m minus 2 plus 1, which is exactly the lowest value, we have here 2m minus 2, and we have here 1. Oh, here must be a minus 1, I think, also. Yes, we need exactly the 2m minus 2 top terms here, which this looks good, yeah. And this does not depend on a2, I'm seeing now. That's maybe the important thing. So we have actually m over 2, not like this, m over 2, the binomial coefficient, times a1 minus 1 faculty divided by a1 minus 1 minus 2m minus 2 faculty plus sum over a2 dp m minus 2 k minus 1 a2. Oops. Yeah, basically this term here. And the values of a2 we can have, we also need to restrict this, because as we said, a2 needs to be somehow bigger than a1. a2 to be bigger or equal to a1 plus minus taking those two m minus 2 lower edges, right? a1 needs to be bigger than this, and a2 needs to be bigger than this. Here's not a plus, here's a multiply sign. And I think there's basically also a maximum for A2, but that depends on m-2 and k-1. And the dynamic programming will just say at some point there that it's 0. So this could be done, and I think this should work for m equal to 50. So the small test could be solved with this, but the big test probably not. I mean, because we have here the sum over all the k's, I'm thinking if I could also reduce this sum over all the A1s, and then I had the dynamic programming just over m and k. Problem I'm seeing here, if I sum over this A1, I have this varying term, and also the sum is varying because I'm actually, if I increase A1, I'm increasing the lower bound on A2. And that makes it somehow unwieldy. To compute this mathematically, what this should be. And I mean, there must be some nice relation which would probably simplify this, otherwise how would you solve for this big M? But I have not the right representation to see how this can fold into itself. If you would have some explicit representation for this sum, you maybe could reduce this and then really unsure here. Stuck already half an hour on this problem. I think in the beginning I laid some good groundwork, but now I really can't see in an efficient way how to compute these combinations of double activated edges. Or is there some probabilistic interpretation that reduces the symmetry in this problem? Sometimes you just need to ask the right question, like how big is the probability that a certain edge is double activated? And then use some kind of independence relation, like that, I don't know, the priority edge 2000 being double activated, the probability for that is, I don't know, independent of the probability that edge 2001 is double activated, but they are usually not independent. What I mean is the case where maybe the edge 2000 is double activated. In those cases, it might be more or less likely that 2001 is also double activated. Are there other events which are somehow independent to each other? So that you can see maybe how one could implement this even for a small test case, I think I will try to implement this and even check if this is even correct. I'm not even sure if this will work, but we'll try, I guess. So just get really two values. I mean, just saying we have two input values. This is something where maybe it could be beneficial to overall test cases actually compute. Where does this dynamic programming actually start? Just thinking. For k equal to 1, is it easy to compute the A1s? If A1 is not the maximum, then this is 0, and if A1 is the maximum, this is how much is that actually? Why does our recursion formula break at that point? Could we not go back to k equal to 0? What does k equal to 0 even mean? So first we could compute the number of possibilities we have to select A1 out of the m edges, which is again m over 2. And then all the other edges need to be lined in such a way that we have no double activated edge, which is actually not trivial in itself. Thinking now if it's maybe really just the probability. What is the probability of a certain edge number being double activated. And can I use that to compute the number of those are not independent. Really not. In this case, it's not even simple. This number of combinations possibilities I have to put the largest value A1. Then the second largest value needs to be connected to that one. So there are 2 times m minus 2 possible edges left. Then the next largest value needs to be connected to one of the 3 we have now connected, which is 3 times m minus 3, I guess. But this could be self-connecting like this is the largest, then we have the second largest, which needs to be connected to one of this, but then the next one could be connected like this, or it could be connected here, and this changes the following multiplication. How is this case even hard? Computing the probability of having one connected group. Is it something to do with how we draw the tree? Draw something like this. One of these edges is double activated. Let's say this one. Then this one needs to activate this one here. This one needs to activate this one. This one needs to activate this one. Means this one is bigger than that one. This one is bigger than that one and bigger than that one. I think I will stop here and jump to future David, who will have a look if problem A and B ran through, and I will also read the analysis of problem C before coming back and explaining to you how C actually works. And maybe I will implement it on screen, but we'll see. Up to future David. See you later. Welcome back. So the competition finished, and after it finished I could upload my solutions, and as expected, problem A and B were both correctly solved by my code. And problem C, I have looked at the analysis. It's quite a bit to consume. I will maybe roughly go in the next 3 minutes or so over the outline, but there are some details which I'm still not really good with, so I think I will maybe actually make an extra video of this, because I have to understand myself a bit more about this solution. But yeah, so the first thing we did was observing that we need to count the number of double activated edges. They call this here an active matching. The number, the configuration basically of edges that are double activated by both of the endpoints, yes. And they did the same observation. That's the number of components is exactly the number of double activated edges. And now one interesting thing is they, instead of trying to count how many combinations there are with exactly k edges, they count how many combinations there are with k or more double activated edges, and call this function g. And then in turn you can use this function to compute the function for exactly k matched edges by using the inclusion-exclusion principle. It's basically, yes, maybe let's draw that inclusion-exclusion principle I am familiar with, so I can at least explain that step. So yeah, let's say they call this function here f from x. X is here actually the graph matching, but for us it's only important basically the absolute, the size of the matching, so how many edges are matched. And let's say we have 3. Yeah, let's say in total we have, I don't know, 7 edges or so, which is not actually a thing for any graph M, because we always have m times m minus 1/2 edges. So maybe 10, like in the m equal to 5 case. And we want to compute for k equals to 7, so 7 double activated edges. Actually, that's not even possible, because I have to think, is this does this even work on just the numbers, or do we really need to have this graph representation at this point? So I think it works the same way. So let's say we have a function which counts the number of double activated edges. I will still call this k greater. So this is a g function actually counting greater or equal to, I don't know, 10, which is the maximum number. So this means actually k equal to 10. And then we have k bigger or equal to 9 and k bigger or equal to, okay, no, this is actually something different. Okay. Wait a minute. So what they are saying is, if we have some graph matching, they call this, for example, is a match for the whole graph, but like if we have two edges matched, this is also a matching for the whole graph. Now they want to compute the function g of this matching, for example, and this should be the probability that these two edges are double activated next to maybe even some other edges. So the probability of this g function is either these are double activated or, I don't know, we need another point. This is a double activated, so the sum of all of these. Now, if we want to compute only for this exact configuration, let's draw this maybe with 6 points here. If we want to have exactly for this configuration our probability, it's the same as taking g of this, the double activated configuration, but then we counted a bit too much and we have to subtract that for all the possible edges we actually doubled, basically. So we have to look at all the sets which have these as a subset. So for example, actually let's put 2 more points in here to get the sum even further. So what is a possible subset of double activated edges would be, for example, this is activated, but also this could be activated. And then we also want to subtract maybe, I don't know, this here. This configuration. But now there's actually, draw it like this again. So these outers are always given. This one had these two connected and the lower one had these two connected. But this configuration now was added here because this is a subgraph of this. It was subtracted here because this is a subgraph of this, and it was also subtracted here because this is a subgraph of this. So we have double subtracted this. So now for correcting that, we need to actually add this again. And this comes down to exactly this formula. You look actually at all the possible supergraphs. So this is a supergraph of this is a supergraph, this and this. And there are more, I haven't drawn them all here. And you add up the g function, which counts the probability of this happening plus maybe some other double activated edges. But for canceling correctly each other, the graphs that are double counted, you actually have to subtract one. And actually this minus sign flips with the number of edges we have. So yeah, like in these cases here, we had one edge added compared to this base x. So this is our x, right? And this is one y, this is another different y, and another different y, and another different y. Here we have exactly the same number of edges. So the magnitude of y minus x is equal to 0 in this case, and the sign is a plus. But here we have y minus x, so y is one bigger actually, has one edge. So we need a minus sign here and a minus sign here. But then for all the configurations where we had actually two edges more, we subtracted them double. Once in this case, basically once in this case, and there's also for these other 4 points, there are other connectivity patterns like this, right? But this again would get a plus sign, basically, because then there's the negative sign with only this edge, and then there's also the negative sign with only this edge. And this goes even further if you have even more points, and yeah. This is basically just inclusion-exclusion principle, this formula, quite useful if you are counting over such subgroups and supergroups. And I think the reasoning here is, well, this is a sum over, well, here you use a lot of symmetry again, because basically you can just rearrange them to always have these two in the first top spots, and yeah, basically, in other words, this g value here is actually the same as this g value, because the function, of course, in the end, everything is permutation invariant, so it really depends just on the number of edges we have in this case and in this case. And this value is, of course, something different, but again, in the end, this is basically just a function of the number of double activated edges we want to have, multiplied with some combination factor for producing these different, how many combinations there are to produce these different supergraphs. So in this case, there will be not only those two, but like I said, here's a fourth combination possible with 3 edges. So from this changes basically, if you do this based on the counts of edges, this changes the -1 factor at this point to not be -1, but yeah, you need to just count. It's a binomial coefficient, and the reasoning now in the following steps is that this g function is actually easier to compute, because there you can actually make some independence assumptions which help you compute this g function value. And they do this actually here. Now, for me to understand this even a bit further, there's a step missing where they say, well, actually, they don't explain how they get this factor. I kind of can see the argumentation, but I'm not 100% clear on it. That's why I won't try to explain it. And then they reduce this even further. I think this is then the part of the function where they actually have this computed over all the possible, basically, transformations between the matching x and all other x's. Yeah, but I'm not 100% sure what exactly this term needs to represent at this point. I have to look closer into it. I wanted to finish this video now, because also here in the last step, they talk about that from G to F, it's a convolution that needs to be applied. Which I also need to understand what exactly, in which form this convolution here they are talking about, if they are talking about the graph representation or the count of double edges representation. I think they're talking about the graph representation. But well, here they're actually looking just at the count of double activated edges, which is at most m12. So maybe it's over the counts, and then I don't see how this exactly is a convolution. And then they also say you can use the fast Fourier transform to compute this convolution more efficient than just doing the naive multiplication and addition as you would normally do. But so I know there's a trick here, but I think I maybe will make just a video just about this fast Fourier transform trick, because I've never used it. I don't know exactly how it works. I just know that there exists a trick, basically. So I think I will make a separate video just about the fast Fourier transform and how you can use it in competitive programming, and then I'll try to make a follow-up video on solving this problem and using in the last step the fast Fourier transform. And hopefully, if I think this is useful, I might even implement it into my code template, so I can use it more easily for this problem then. But yeah, in the end, a really hard problem, and I'm not the only one who thinks that, I guess, because it's really just 8 people who got a full score, which is really not that much. And if you look at who solved, I don't know, can I sort for this problem? Not really, but it seems only the top 9 have actually solved this one. And then I think the scores are just too low for anyone else to have solved the big one here. Maybe there's one person or so who actually managed to solve this, but well, I doubt it, because it's a really hard problem. You can see that for first 8, they managed it. They still took quite some time. You can here see the fastest time was 1 hour 10, so he's probably quite good. But also took for the first problem 26 minutes. So actually this one was quite fast solved by him. That's impressive. But then you can see this times go from 1.5 hours. For a second place, this is like super slow usually, but this competition was hard. The full score was very hard. You can here see not even that many have tried it even. Yeah, 1% solved the big one, 2% solved the smaller one. So kudos to all who solved those. And if you got to the top 1,500, congratulations, you will have advanced to round 2. So that will be the next round in 2 weeks, where I can also participate and actually have a go directly solving the problems again. And I will do some practicing before that. So maybe look out for new videos solving a few of the past Kickstart problems of round B. So yeah, hope you enjoyed the video. Look out for my intranets upload, and have a good weekend. Bye.